Okay, I'm really excited to talk to you today about thermodynamics. And I'm excited to talk about thermodynamics because we're going to be ultimately relating this to chemical equilibrium, which is a really fun, kind of fascinating blend of both physics and chemistry. And it gets us into one of my favorite concepts in chemistry, which is entropy, which is kind of the study of disorder or chaos, which I'm very excited to talk about. So before I can get there, though, I want to do kind of a quick introduction to thermodynamics as a field, kind of some of the variables that you'll see. Hopefully this is a review. It's really geared towards, maybe you've seen some of this material before, and you're just getting a little bit of a reminder about what the different concepts are. Or if you've never seen it before, then this will give you kind of a foundation for moving to the more complicated sides of thermodynamics in a chemical context, which of course is what I'm, as a chemist, interested in. All right, so the field of thermodynamics really straddles the boundaries of both physics and chemistry. Like I mentioned, thermo referring to heat, dynamic referring to change. So we're looking at the changing heat, the changing energy of a system. And in this case, we're usually looking at a chemical system. You can look at any system. When we define a system, we're talking about something specific that we're studying, as opposed to its surroundings, which is kind of everything in the vicinity of that system. So I could have, my little beaker here, and here's my system. Whatever's going on in the beaker is what I define as my system. The surroundings then could be the surroundings of my beaker. It could also be that the solution within my beaker, the chemical reaction, could be the system, and then the water surrounding it could be the surroundings, right? If the water itself isn't involved in the chemistry, then that surrounding water could be something that we're looking at, because this is all about the change in energy, and we usually will perceive that then in a chemical context as a change in temperature. So let's do some review of concepts then. First law of thermodynamics is usually the one that people think about as the law of conservation of energy, right? So that, you can't create or destroy energy in some sort of chemical process. And mathematically, this is the way that we look at it, with the change in U, which is our internal energy, which I've never understood why it's a U for the variable. But there you go. I think they ran out of variables at some point. Q is our heat. W is work. So this essentially says that the total energy of a system remains constant, and any energy transfers in the system are going to be equal to the total internal energy of the system. Okay, so heat can flow in or out of the system. The heat can be lost or gained by system. And if heat is being lost, then we say that the heat is negative, right? So it's, by definition, or the way that we define these terms, it's negative. I think of losing heat as a negative thing for the system, and the heat is coming out of the system, so it's negative. If it's being gained or absorbed by the system, then we say that that's positive heat. So the internal energy of a system can really is dependent on the way that we're defining our system itself. When we as chemists think about internal energy, it's often the energy that it takes to make and break bonds. It can be more than that depending on how you define the system, but there's a lot of energy that that is both required and released when bonds are being broken and made. Okay, the work is pressure volume work. So that's also written, so work is equal to kind of how much the change in the volume of the system is. This is usually more related to thinking about gases. We do tend to think about gases when we're thinking about thermodynamics and systems in the gaseous state, because we're usually working at higher temperatures, so that makes sense for some of these. So this is pressure volume work, which really has to do with work either being done to the system. So this is work done to, or work done by the system. So I always kind of think of this as a Rube Goldberg kind of device. So if I start a process, that is work that's being done to the system, but if then the system is self-perpetuating, self-propagating in some way, then that is work that is being done by the system. And so we're going to have to account for all of that work that's being done. Work in a scientific context is just is overcoming some sort of force. So that could be something like even just picking up my pen, right? I'm doing work on this pen because this pen isn't spontaneously going to move on its own. I have to apply some energy to the system, the kinetic energy of my hand here, and the energy of the electrostatics and everything that's going into kind of this particular process. I have to put the energy in, but then once the energy goes away, once I remove the force that is overcoming the force of gravity here, so I'm holding up the pen, I'm using my muscles to do that, especially after being in quarantine for so long. My muscles are weakened, so this is definitely harder than it should be. So I'm holding up my pen here, and if I was to remove this force that's overcoming gravity, then the pen is going to go back down to its ground state, right? So I had to apply some energy to get it out of its ground state. That increases the potential energy, which is the energy of position of an object, and then that potential energy can be converted back to kinetic as it falls back to the ground state, the lowest energy configuration. So as chemists, we're interested in the chemistry, the chemical reactions and the energy there. So that would be H for enthalpy. Enthalpy is the energy of a chemical process. And we also call this the heat of reaction, and there's a relationship between the heat and your enthalpy. It's really about the change in enthalpy. Enthalpy is a state function, and enthalpy is equal to the internal energy plus the pressure and the volume of that system at any given time. So again, this is a state function. Actually, all of these are state functions. A state function is a function of a material or a function of a system that is independent of anything that has come before it or after it. It's just a snapshot, essentially, of what's going on in that function at that very moment. Now, that's, all well and good, but as a chemist and as a scientist, it's more interesting to me to look at the change in these things. So if I'm looking at the change in enthalpy, then that's going to be equal to kind of the sum of all of the molar quantities of all of the heats of formation of my products minus the sum of all of the molar quantities of the heat of formation of my reactants and H sub F here, this is heat of formation which means the amount of energy that it takes to make that particular compound. And these are all look-upable in thermodynamic tables. The degree symbol here means that we're at standard conditions. So this is actually the delta H, kind of, if you think about that little degree symbol, at standard conditions. Which are defined as 1 atmosphere of pressure and 25 degrees Celsius. And when you start to mess with that, then you can mess with your delta H's, and there's ways to calculate that, there's ways to measure that, but anytime you're looking up any thermodynamic information in tables, then this is going to be the parameter. The big one there is temperature. All right, now the relationship between enthalpy and heat then is that the Q that we talked about here for the total internal energy, the change in the total internal energy is equal to the heat lost or gained plus the work that is being done to or by the system. The heat is equal to the change in enthalpy of the reaction. So we talk about this again as the heat of formation or the heat of the chemical reaction. And that's just one of the important quantities that we get from a chemical reaction. Now, if this quantity, in the same way that we're losing or gaining heat up here for Q, if delta H is negative, we say that the reaction is exothermic, or exergonic is another way to say that. So you see them both interchangeably, exergonic and exothermic. I like exothermic because exo looks like exit, therm, of course, referring to heat, so the heat is exiting the system. It's an exothermic reaction, and the delta H, when it's positive, means that it requires more energy to do this reaction than it releases, and we say that it's an endothermic reaction. And again, endogonic, endothermic, kind of that prefix end means that something is coming into, and again, I like thermic as opposed to gonic because I like the thermal kind of side of things. It reminds me of heat. So heat is coming into the system. It requires more energy than it releases, as opposed to exothermic, which releases more energy than it requires. Now, kind of where we're moving with this, again, this is a little bit of a review of terms, it's a review of concepts. Where we're moving with this is to talk about the spontaneity of reactions. And for a reaction to be spontaneous, then there have to be certain combinations of these different energetic quantities to be true in order for a reaction to occur in the first place. So it's funny because we learn about chemistry and we learn about chemical reactions and we learn about chemical processes, and we say, oh, well, they go in this direction, or it favors the reactants, or it favors the products, or it shifts this way. And we don't really understand what that means from an energetic standpoint, but that's kind of where we're headed, at least in this kind of next series of videos. So I hope that you'll stick with me and ask questions as you have them.